All right, I wanted to start here. I know this was the ending of the last lecture. I wanted to start here because I want to point out something before we kind of move forward. If you notice that when we were learning about these covalent bonds and how to draw them, we were just going through and drawing out our dot structures, and then we were trying to find the single electrons that were by themselves and then pair them up to figure out where the bonds go. And really, it's not too bad when you're working with simple molecules like two O's or two N's, or even H2O to a certain degree is not too hard to do. But if you get anything more than that, if it gets any bigger than that, this becomes really sort of a difficult way to draw these structures. So what we're going to do today is we're going to learn a better, more reliable way of drawing these structures that will work no matter how complex that the molecule might get. Okay, so these structures that we are drawing are called Lewis structures, named after the man who kind of came up with this whole idea of how to draw them. Okay, so the rules for drawing Lewis structures for covalent compounds, we're going to go through them one at a time. It's really more steps, I guess, than rules, but kind of break this down into steps so that you can draw out a correct Lewis structure for a molecule every time, no matter what. Now, we're going to use water. I know we've done water's structure already, but we're going to use that as our example just to show you how this works, and then we'll do some other ones also, okay? All right, so when we're doing a Lewis structure, when we want to draw out a molecule and figure out where the bonds are, and where are the lone pairs and all that kind of stuff, one of the very first things you have to do is you have to figure out how many valence electrons total do you have between all of the atoms that are going to be in the molecule. So, for example, let's say we're going to do water, right? Water is H2O, so it's got two H's and an O. Well, we would have to know how many valence electrons are in each of these atoms, and the way that we know that is because we look up what group they're in on the periodic table. So once again, unless you have all of this memorized, and most of us don't, then you probably need to have a periodic table available that you can look at right now. Again, if you need to pause, you can do that, but please make sure you've got that out so you can refer to that as we're going along. Okay? All right, so for H2O, we want to figure out how many valence electrons total we have. So we first would look up H. H is in group 1 on the periodic table, so it has one valence electron, but there's two H's, so that's two valence electrons from the H's. And then we look up O. Oxygen is in group 16 on the periodic table, so it has 6 valence electrons. So we have 2 from the two H's, and then we have 6 from the O, and that makes a total of 8 valence electrons. Now, why do we do this? We do this because, remember, they're sharing their electrons. The maximum number of electrons that can be shared are the maximum number that they all have to begin with. So if we're going to create a new molecule that has two H's and an O in it, then we have to make sure that that new molecule doesn't have more than 8 electrons total, valence electrons total in it. All right, step 2, write the symbols for the atoms in the molecule. And we're going to write them so that one of them is in the middle. Now, if you want to figure out which one's going to be in the middle, usually you're going to figure out which one is the least electronegative element. Now, electronegativity was one of our trends of the periodic table that we learned back in chapter 6 last semester. So, electronegativity is the ability of an atom to attract electrons to itself. The least electronegative is the one that ends up in the middle of a molecule, usually. And the way the trend works is, if you're looking at the periodic table, electronegativity increases as you get closer and closer to fluorine on the upper right-hand corner. Okay, so it increases as you go across from left to right, and it increases as you go from bottom to top. So that means that things that are further away, nonmetals that are further away from fluorine, are the ones that generally end up in the middle. Like carbon often is in the middle, or phosphorus would be in the middle, or sulfur would be in the middle. Those would be nonmetals that are further away from F. Well, I don't have any of those here. Now, if you looked up the electronegativity of H and O, you'd say, well, H is much further away from fluorine than O is, so H must go in the middle. But remember, H only has one valence electron. So how many bonds could it ever make? How many places could it ever share an electron? Well, it could only share in one spot. It could only form one bond. But if an atom is going to be in the middle of a molecule, it has to form at least two bonds. It's kind of like if I asked you to stand between two people and hold both their hands. If you had to stand between two people and hold both of their hands, one arm is going to be holding the hand of one person, and the other arm is going to be holding the hand of the other person. So you'd have to obviously have two arms. If you did not have two arms, you could not serve that purpose, right? So since H can't go in the middle, that's why I said usually the least electronegative atoms start in the middle, but H can never start in the middle. So O has to be the one that goes in the middle. So we're going to write out what we call a skeleton structure. We call it a skeleton structure because we haven't put anything in here yet. All we did is we figured out the order. We figured out that O has to be the atom in the middle, and that all of the other atoms, which happen to be two H's, are going to be on the outside of the O. Where on the outside of the O? It doesn't really matter right now. Okay, it doesn't matter where on the outside of the O. You just need to make sure that they're all connected to the central atom. Third step, we're going to start by drawing one single bond, one dash, in between each pair of atoms. Even if we don't have a clue whether we need them or not, or whether they're going to be double bonds or triple bonds sometime, we're going to start making them all single bonds. So in our skeleton structure for water here, we're simply going to put a bond between the O and the H, and a bond between the H and the O. Okay? Bond on both sides. Again, we haven't completed this. We don't know if it's going to need anything else besides single bonds, but we always start this way. All right? All right, step 4. Now we're going to go through and we're going to add in lone pairs around each atom. So each atom has its octet of valence electrons, because that's what makes it stable. That's the whole reason it's actually bonding with other atoms, because when they share, the atoms want to have 8 valence electrons. Except for H. Don't forget, hydrogen wants to be like its nearest noble gas, which is helium. Helium only has 2, so hydrogen only wants to have 2. So if we go back to that original structure that we had, right? We had, and I'm just going to draw it in for the moment here. We had one single bond here, and we had one single bond here. Now, the hydrogen here is just happy as a clam. Why? Because it's got 2 electrons around it from this bond. Remember, every bond counts as 2 electrons. So this hydrogen already has 2. It's happy. It doesn't need anything else. This hydrogen on the other side is also very happy because it has its 2. So it's good. But the oxygen here in the middle is just like most of the other elements in the periodic table. It wants 8. And if it wants 8 and it has 2 on this side and it has 2 on this side, that means it only has 4. It needs 4 more. So we draw in lone pairs. That means that we're going to draw pairs of dots around the outside of the oxygen. That way, the oxygen now has 2, 4, 6, 8. And now the oxygen has all the electrons that it wants. Now, I'm going to get rid of my ugly drawing here, and then let's put in the neater version. All right. Now, at this point, you need to decide whether you've done this right. And to figure out if you've done this right, you're going to ask yourself 2 questions. Do this internally. Don't say it out loud because it sounds weird when you talk to yourself, right? Ask yourself 2 questions. A, are all the atoms happy, right? Did all the atoms get the number of electrons that they wanted to have? So we said the hydrogens always want 2, so each of our hydrogens each have their 2. They're good. The oxygen wants 8. It has 2, 4, 6, 8 around it. Therefore, yes. So then the other question, which is really important, did you use the same number of electrons that you started with? So you remember back at the beginning, the first step, we counted out the number of valence electrons that they had total. And the 2 H's and the O had a total of 8 valence electrons. So did I just use 8 electrons to make this structure? I put 2 here, I put 2 here, I put 2 here, I put 2 here, that's 8. So if you answered yes to both of those questions, then I guarantee you, you have the correct Lewis structure. You have drawn the molecule correctly. Now, if you answered no to the first question, are all the atoms happy, then you simply just didn't follow all of the steps correctly. Go back and make sure that they all have all of the lone pairs that they might need to be happy. But if you answered no to the second question, did you use the same number of electrons you started with? It's possible that you did everything right and you still answered no to that. And if that happens, that means that the single bonds that you started with are not the kind of bonds you need in this structure. That means you're going to need either some double bonds or some triple bonds to make this work. Okay? And I'll show you how that's going to work as we go. Obviously, the water molecule didn't need anything else. It was fine the way it is. And to tell you the truth, most of the time, it will be fine the way it is. Okay? So that's the steps that you're going to follow. First step, count up how many total valence electrons there are. Second step, figure out what atom is going to be in the middle of the molecule. Third step, give everybody single bonds. Fourth step, give everybody lone pairs, unless they're hydrogen. And then ask yourself those 2 questions. Okay? It's a foolproof, guaranteed, no matter what, you will get the right answer if you follow those steps. So why do chemistry students in my class not get the right answer every single time? Because they get lazy and they don't want to follow each step by step. And they want to skip things and they want to go right to the end and think that they know what the answer is. And that's when people get wrong answers. Okay, so if you follow these, it works. Now, I have some examples here, some other examples that I want you and I to try together. Okay, so this is important. This is part of what you're going to be writing down. Right? I want you to go through, and some of it I'll kind of lead you through, and some of it I want you to try on your own. Okay? All right, so let's start with this first one, I2. Okay? So we're going to go step by step. First step is we need to figure out how many valence electrons are in the molecule I2. So I have 2 I's, so obviously I need to know how many valence electrons are in one iodine. So you have to look up on your periodic table, where is iodine? So if you look up iodine, iodine's in group 17. So if it's in group 17, then it means it has 7 valence electrons. But there's 2 iodines here. Therefore, it has a total of 14. Now, I like to write that down just so I keep track of that, right? Because at the end, we have to do a count, and we have to make sure it matches with what we started with. So we're starting with 14 valence electrons. All right, second step. We decided second step means you have to figure out which one goes in the middle. Is it the I or the I? Yeah, you're right. That doesn't make any sense. There's no middle, right? There's just 2 I's. There is no middle. To have a middle, you have to have at least 3 things. So in that case, we don't have to worry about what goes in the middle. If we just have two eyes, then just draw two eyes next to each other. Remember, you got to leave enough space in between that we can draw bonds. All right, so I did step number 2. Step number 3 was put single bonds in between each atom. Well, I only have 2 atoms to put a bond between, so one single bond will work. 4th step, start adding lone pairs around each atom so that each atom gets what it wants. Remember, everything wants 8 except for hydrogen that only wants 2. So that means that iodine wants 8. How many electrons does it have right now? Well, it only has these 2. Therefore, it's going to need some lone pairs. So if I put 2 here, and if I put 2 here, and if I put 2 here, now this iodine has a total of 8, right? There's 2 from the bond plus these 2, and these 2. So that's 8 total. This iodine wants the same thing, so we're going to put some lone pairs around this iodine. Okay, now that iodine has everything it wants. It has 8, 2, 4, 6, and then 2 from the bond is 8. So we now ask ourselves the 2 questions. Did we make all of the atoms happy? Do they all have the number of electrons they want to have? Yep. And did we use the number of electrons that we started with? So let's count. We have 2, 4, 6, 8, 10, 12, and then the 2 in the middle make 14. So that must be the correct Lewis structure for I2. Obviously, that was a really simple one, but it's going to happen that way. They're not always going to be really, really complex. I want you to be able to understand how to do that. So we start simply. All right, let's try the next one. The next one is PCl3. All right, so first thing I want you to do, pause this and determine how many valence electrons are in PCl3. Okay, you've done that, hopefully. You figured out, you looked up P. P is in group 15, so it has 5. Cl is in group 17, so it has 7, but there's 3 of those. So 7 times 3 is 21, plus the 5 from the P is 26. So this has 26 valence electrons to begin with. All right, next we have to figure out what goes in the middle. Is it going to be the P or is it going to be one of the Cl's? Right? So remember, our rule said usually the least electronegative element goes in the middle. So out of P and Cl, which one's furthest away from F, from the fluorine? Well, P is, right? P is the phosphorus is the furthest away, so it's the least electronegative. That means it's the one that's probably going to be in the middle. Now, another clue would be, well, there's only one P and there are 3 Cl's, so it makes sense that the one P is the one that's going to be in the middle, right? So we're going to put the phosphorus here in the middle, and that means that the 3 Cl's then have to go around the P. Where? It doesn't really matter where right now. Pick 3 sides. I'm going to put one here, I'm going to put one here, I'm going to put one here. If you had put one on top instead of the bottom or whatever, that would have been fine too. All right, step 3. Step 3 says that we put one single bond in between each pair of atoms. So single bond here, single bond here, single bond here. Step 4, add in lone pairs around each atom so they get what they want. Remember, everything wants 8 except for hydrogen. Well, none of these are hydrogen, so they all want 8. So how many does this chlorine have right now? Well, it only has these 2 from this bond. So it's going to need another 2 here, and another 2 here, and another 2 here. Now this chlorine is going to be the same, right? It's going to need the same number of electrons. So is this chlorine. So we're going to draw in lone pairs around everything. Really, everything is going to be surrounded by lone pairs almost all the time, except for hydrogen. Hydrogen never needs any more lone pairs. And then the phosphorus here in the middle has 2 from this bond, 2 from this bond, 2 from this bond. That makes 6, but it wants to have 8. We know that. So we're going to put 2 more here. And now we ask ourselves the 2 questions. Are all of the atoms happy? Did they all get the 8 that they wanted? Well, we just made sure of that. But that's why you ask yourself that question. You make sure that you did that step. And then finally, did we use the same number of electrons we started with? So we started with 26 valence electrons. Let's see, let's count them up. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and then 22, 24, 26 with the bonds here in the middle. So 26 matches what we started with, therefore we don't have to do anything else to that structure. That must be the correct Lewis structure for PCl3. Okay. All right. Now, for the tricky one. It doesn't look like it would be very tricky. It looks like it'd be really simple, but this is the tricky one. So once again, what I want you to do for C here, for CO, that's a carbon and an oxygen, CO. I want you to look up carbon and oxygen and figure out how many valence electrons that is total to begin with. So pause and go do that. Okay. So you looked up carbon. Carbon's in group 14, so it has 4. Oxygen's in group 16, so it has 6. 4 plus 6 is 10. So we're starting with 10 valence electrons. Next, step 2, we have to determine what goes in the middle. Well, this is one of those ones, again, we only have 2 atoms, C and O. There is no middle. It's just C and O. So I have C and I have O. Third step, what do we put there? 1 single bond, you're correct. 1 single bond goes there. Fourth step, what do? Put in lone pairs so everybody's happy. So this oxygen needs more lone pairs, so it has 8 total electrons around it. Same thing with the carbon, right? Carbon also wants to have 8, so it needs lone pairs. Okay, at this point, ask yourself the 2 questions. Did we make all the atoms happy? Do they all have the 8 that they want? Yep. Did we use the same number of electrons we started with? Well, let's see. We've got 2, 4, 6, 8, 10, 12, and the 2 in the middle make 14. Whoa, we overshot. We only wanted 10 to use here, and we used 14. So this can't be the correct structure. Okay. All right, so how do we solve that problem? Well, we said before, the reason that would ever happen is because it must not be a single bond we need. We must need a double or a triple bond to make this work. So the way we're going to do this is you find yourself in this situation, add another bond. So instead of making that a single bond, I'm going to make that a double bond. You could probably draw yours straighter than I did with my mouse here. That's pretty sad. But that I draw another bond in, and then every time I add a bond, I have to erase 2 lone pairs, 1 from each side. So if I draw my bond here, then I have to draw or erase a lone pair from that side of the bond and from this side of the bond. So every bond erases 2 lone pairs. All right, let's do a little count now. All right, well, we have to ask 2 questions again. We have to make sure both questions can be answered. First of all, do each of the atoms have what they want? Are they both happy? So the carbon wants to have 8, right? So there's 2 here, there's 2 here, there's 2 here, there's 2 here, right? Because there's 2 bonds here. So that's a total of 8. Well, the oxygen has the same thing, right? It has 2, 4, and then the 6, 8. So that makes it happy also. So yes, we're good there. Have we gotten it to 10 electrons total, though? Well, that's 2, 4, 6, 8, 10, 12. Nope, not yet. Okay. So I have to keep going with this idea of adding bonds. So I'm going to go ahead and add another bond. So now I'm going to make this a triple bond. And every time I add a bond, what do I have to do? I have to erase a lone pair from both sides of the bond. So I added a bond here. That means I have to erase a lone pair on that side and a lone pair on this side. Now, ask ourselves the two questions again. I know that gets tedious, and this is where people get in trouble because a lot of students would be like, oh, I don't want to do this whole thing again. I'll just assume it's right. Well, no, don't just assume it's right. Make sure, because this is where mistakes get made. So we need to make sure, are both of the atoms still happy? So this carbon has 2 from this lone pair, plus 2, 4, 6 more from these bonds. So 2 plus 6 makes 8. So this carbon's happy. Yep. This oxygen over here, same deal. It has the 2 from the lone pair plus the 6 from the bond, makes 8 around it. So the oxygen's happy. And did we use 10 total electrons? So I had 2 on this side, I had 2 on this side, and I have 6 in the middle. 6 plus 2 makes 10. So that must be the correct structure. CO must have a triple bond in it. Okay? So when we're talking about doing double and triple bonds, you won't necessarily know they're going to be double and triple bonds when you start. Notice that the steps say always start with a single bond. To tell you the truth, most of the time the single bond will work. But of course there are going to be times when it's not going to work and you're going to have to go through this process of adding bonds and erasing lone pairs. This is also another good idea to get in the habit of using a pencil because it's really hard to do this with pen. All right? Okay. You know what? I don't need the pen right now. Let's talk about some other kinds of Lewis structures that you might see out there that you need to be prepared for. Because not all Lewis structures are going to go nice and simply as those do. For instance, there are sometimes molecules in which the shared electrons are actually all going to come from one of the atoms, and the other atom doesn't share at all. It's what we call a coordinate covalent bond. Now, why is that important? Because it turns out that polyatomic ions are actually coordinate covalent compounds that have a charge. So in other words, they're a group of atoms that all got together to share their electrons, and then they either realized that they had too many electrons and they got to give some away, or they didn't have enough electrons when they all started sharing with each other and they had to gain some from some other element out there. So we can draw Lewis structures for polyatomic ions, but we have to keep in mind one little difference. So the charge on a polyatomic ion is going to affect the number of electrons we start with. So here's an example of this. Let's say that we wanted to draw the Lewis structure for this polyatomic ion, NH4, with a positive 1 charge. If you remember your ions, and hopefully you remember some of them at least, that's called ammonium. So the ammonium ion, NH4 with a positive 1 ion. Let's count up the number of valence electrons that we have here. N is in group 15, so it has 5. H is in group 1, so it has 1, but there's 4 of them. So 5 plus 4 makes 9. But the positive charge here, remember, charges always refer to how many fewer or how many more electrons that group has. So a positive charge means it has 1 less electron than normal, because electrons are negative. So we have to actually subtract an electron from 9. And that tells us that we're actually starting with 8 valence electrons. Now we can do the rest of this as normal. So the next step would be what goes in the middle, the N or one of the H's. Well, we learned that H's can't go in the middle, so the N has to go in the middle here. Okay. So put the N in the middle. All of the H's would have to go around the outside of it. We put 1 single bond, that's our steps, right? We always have to follow steps. 1 single bond between each pair of atoms. And then we put in lone pairs around everything that still needs more electrons. Well, remember the H's don't need any more than 2 electrons, so they're good. They don't need lone pairs ever. Don't add lone pairs to H's. And the N here in the middle, the nitrogen here in the middle, already has 2, 4, 6, 8 around it. It doesn't need any more either. So it doesn't need any lone pairs. So I didn't even have to add any lone pairs. Everybody's happy. And then I have to ask myself the other question, which was, did I use the same number of electrons I started with? Well, I started with 8. Did I just use 8? Well, it's 2, 4, 6, 8. Yep. So this is the correct Lewis structure. But I have to let somebody know when I draw this structure that this isn't NH4. This is NH4 with a positive charge. So the last thing we're going to do is when we draw Lewis structures of polyatomic ions is we're going to put some brackets around the outside of that structure, and we're going to put the charge on the outside of it to show that that whole structure doesn't have the number of valence electrons that you would think it did. Okay? So again, this happens only when you're talking about polyatomic ions that have a charge. Other exceptions to the rule. There are a few, not common, but there are a few times when you can actually have an element take more or less than an octet of valence electrons. We always said an octet is optimal, right? 8 is exactly what it wants. And that's certainly true, but that doesn't mean that it has to stop at 8. If an element is in period 3, 4, 5, 6, or 7 on the periodic table, that means not only does it have an S, not only does it have a P, but also has a D and possibly even an F orbital. And generally we don't talk about the electrons that are in the D or the F orbitals. We don't worry about them. But they are there, and therefore technically you could take more than 8 electrons in those cases. And so I want to show you what that would look like so you're prepared in case you see those. Okay? So we're going to do 3 examples here. First one, PCl5. Right? So PCl5, we have to follow the steps just like we did before. So the first step was count up how many valence electrons total we have in PCl5. You should be able to do that by now. So go ahead and count those up and then come back to this. Okay, you've got that figured out. The phosphorus here is in group 15, so it has 5. The Cl is in group 17, so it has 7. But there's 5 of them. 7 times 5 is 35. 35 plus the 5 from the P makes 40. So there are 40 valence electrons to work with here. Sounds like a lot, and it is. Next, we have to determine what goes in the middle. Is it the P or one of the Cl's? So once again, whatever element turns out to be furthest from F. Well, P is furthest from F. So P is going to go in the middle. So the phosphorus goes in the middle. And then I have 5 Cl's. All 5 of them have to attach to the middle. Normally, we think of these symbols having 4 sides to them. And you're right, that's generally the rule. We think of them as having 4 sides. But if we have 5 Cl's to put there, we got to put it somewhere, so pick a corner. It doesn't matter which corner you pick. All right, next we have to put one single bond between each pair of atoms. That means I need a bond here, 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 and here. Now already there's probably little alarms going off in your head going, that doesn't look right. That's not right. There's an octet rule, right? The octet rule says that everything wants to have 8. Already before I go to any other steps, I can tell that the phosphorus here in the middle is taking on 2, 4, 6, 8, 10 electrons. That's more than an octet. That doesn't make any sense. But if you look at where phosphorus is on the periodic table, phosphorus is in period 3. If it's in the 3rd period, that means it has a 3s, it has a 3p, and technically it also would have a 3d. And therefore it could take more than 8 valence electrons on at one time, because it could start stuffing some of away into that d orbital, okay? Now, we're not done with this yet. Just because we determined that the phosphorus can take 10, like it's showing right now, doesn't mean that everybody else has to go with, the wrong number. All the chlorines still want to have 8, so I have to put some lone pairs around them. So let's do that. Let's draw those in. Right. And this chlorine needs to have some, and this one needs to have some. This is probably a little bit easier if you've got a writing utensil that's not a mouse. But this is what I got to work with, so it takes me just a moment. All right. So, did we make all the chlorines happy? All the chlorines have their 8 valence electrons, so they're all good. Did we make the phosphorus happy? Well, no, but there wasn't much we could do about that, right? I mean, if the formula is PCl5, it's not a misprint, that's what it says, so we had to put CLs around all the way around it. It has to take 10. So going with that idea that phosphorus can take 10, so it's just going to take it, do we have 40? Well, I have 2, 4, 6 around each of the CLs. So 6 times 5 CLs is 30, plus I have the 10 that comes from the bonds here in the middle, so 30 plus 10 makes 40 electrons. This has got to be the correct structure. Yeah, it looks a little bit weird, right? But it is possible. All right, let's try another one. BF3. I want to do this with BF3. So again, I need you to look up the number of valence electrons for BF3. All right, you should have looked up the B should be in group 13, right? So it has 3. And the F is in group 17, so it has 7, but there's 3 of them. So 7 times 3 is 21. 21 plus 3 is 24. So this is 24 valence electrons that I'm starting with. Oops. All right, now what's going to go in the middle? Well, it's kind of obvious the B is going to go in the middle. It's certainly the furthest away from F. So B is going to go in the middle. I have 3 F's to put around. Where do you put them? Pick 3 sides. It doesn't really matter. Then I put 1 single bond in, right? We're getting used to these steps. 1 single bond each. And then make everybody happy. So everybody wants to have 8, right? So let's start putting in our lone pairs around everything. We're all good. We're all cool. Got our... And we're going to give 2 to the B, right? Because the B only had 6. So the boron wants to have 2 more, so it has 8. All right. So again, now we ask ourselves the 2 questions. Did we make everybody happy? Does everybody have the 8 that they want? Well, the F has 8, this F has 8, this F has 8, this B has 8. Cool. Well, that seems pretty simple. Now we got to ask the second question. Did we use 24 electrons to do this? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Oh, wait. I know how to solve this, right? We said earlier that if we ran into this problem where we have too many electrons, we just start adding in like double bonds. That'll fix it. Except we got a problem here. I want you to think about what fluorine looks like when it's by itself. If I just draw fluorine when it's by itself, we know that fluorine starts with 7 valence electrons. So it would have 2 here, it would have 2 here, it would have 2 here, and then it would have 1 here, right? So how many places can fluorine make a bond with something else? Well, it's already got 2 here, it's already got 2 here, it's already got 2 here. This is the only place, right here, it's the only place where a bond can form for fluorine. Another way to say that is that fluorine can only form a single bond. So if no double bonds can ever go to fluorines, then where could I put a double bond here to make this work? I don't have any choices. There's no place to put a double bond. But I got to get this down to 24. So what do? Well, that means that somebody's just going to have to lose one of those lone pairs that we drew in. So who's going to go without their 8? Fluorine, who's the most electronegative element on the entire periodic table and always gets what it wants, or poor little boron. Well, you can tell already, boron is going to lose this battle. If somebody's going to have to lose electrons out of this structure, it's going to be boron. So I'm going to go back and I'm going to erase that lone pair that I had put on the top of boron. Now, it doesn't seem fair. How many does boron have here? It only has 6. But the only way that you can make a structure with B and 3 Fs is to make this happen, right? Fs can't take double bonds. B's going to get screwed in the deal. It's the way it works. All right, I want you to try the last one on your own, completely on your own. You do the whole thing and figure out what it's going to look like. And then I'll draw it for you in just a moment, okay? All right, at this point, you should have drawn your own. So S is in group 16, so it has 6. F is in group 17, so it has 7. But there's 6 of them. 7 times 6 is 42, plus 6 more is 48. So this thing's got 48 valence electrons to work with. What goes in the middle? Well, obviously the S is in the middle. And then I have 6 Fs to put around the outside of it. So once again, we usually start with their normal 4 sides. But then since I have 6 of these, I got to pick 2 corners to put Fs in. Does it matter which 2 corners you pick? Not really. I always try to be symmetrical when I make mine. Put 1 single bond in, 1 single bond here, 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 and here. Wow, that's a lot of electrons. The sulfur is now taking on 12 electrons. But remember, sulfur is in group, or not group, period 3. If it's in period 3, that means it has 3 energy levels. The third energy level is a 3s, a 3p, and a 3d. It can take more than 8. The fluorines, the little spoiled princesses that they are, get exactly what they want every time. So they get their 8, so we still have to draw in all of the lone pairs around them. Right? Make everybody else happy besides the sulfur. And then we go through and we do our count at the end. Did we end up with 48? Well, I have 6 around this F, and I have 6 F, so 6 times 6 is 36. Plus the 12 from the bonds, 36 plus 12 is 48. So that's what your structure should look like. Okay? So this is what we're talking about when we talk about drawing a Lewis structure. Follow these steps, the 5 steps that we just talked about. And then, if it's a polyatomic ion, you have a little extra to do. And then it could be one of these exceptions to the octet rule also. You have to keep track of that and just make sure that you know that that could end up like that every once in a while. Okay?